Hello pre-calculus folks, this is Mr. McAllen and we're going to work on two types of problems today for a work that we're going to do tomorrow. As you can see here, we have a polynomial f of x, and one of the things that we want to be able to do when we have a polynomial is we want to be able to determine what are the boundaries for the zeros that we're looking for. We don't want to just randomly search for zeros. We want to be able to know between what value and what value or on what interval we should be searching for our zeros. So one of the things that you would look for upon synthetic division is you would look for, if you did synthetic division with a possible root value, if you saw an alternation of signs, and I'll explain this through an example. If you see signs alternate on your synthetic division result, then you would know that you have reached the low bound or the lower value for where your roots will be found. And if you see no alternation in signs, let's say all your values are either all negative or they're all positive, then you would know that you've reached the upper bound. So on Desmos, I plotted this polynomial so that we could see what it looks like to begin with. So Desmos shows a polynomial here where our roots are only going to be found on the interval between -2 and 1. But as I said earlier, in the old days, we didn't have tools like Desmos. We had to do things more, we had to just have these little tricks from algebra to try to figure out where the roots would be. So, so this sign trick is actually, or the sign method is actually the way that we would be able to justify that we know we've reached a lower bound or an upper bound. So just hypothetically, let's pretend that we're going to try out a root for this synthetic division. So I'll put my coefficients out, 3, 4, -5, and -2. And if I try a root, let's say, from what Desmos was showing, if I try a root, let's say I try -3 for my root, and I perform synthetic division, so I bring the 3 down, -9, this will be -5, this will be 15, so I'll get 10. And then I'll have -30, so this will be -32. When I inspect my synthetic division, I see I had alternation of signs, so this tells me that there's no root to be found less than -3. And this is really helpful because if we were checking for roots and we had a possible list of roots to check, we would definitely, after we saw an alternation of signs going on for a possible root check, we would stop looking at values lower than -3 to find a root. And so let's put a root in that's obviously not in its upper bound. So we'll try out. Let's do the same coefficients. We got 3, 4, -5. And -2, and let's say we try a root like 5. We know the root is not, the roots are less than 5, but if we try that out, we have 3, then we get 15, this will make 19, and then we multiply 19 by 5 and we have 95, and this makes 90, and clearly this is going to be like 450, so we're going to be at 448. As you can see, we have all positive values for our synthetic division. Our remainder is 448. Because we have no alternation of signs, we know that we can conclude that there is no root greater than x equals 5. So this is using the sign test to tell us where our lower bound is and our upper bound. So in some of the problems that we have, or that I give you, I'm going to simply ask, prove that, I could phrase this question, prove that for this polynomial that the roots are bounded between -3 and 5, or they're going to be found within that interval. So you'd use -3 as a lower check, you'd use 5 as an upper check, and you would be looking for alternation of signs for a lower bound and no change in sign for the upper bound. Okay, so now we're back. I had to pause the video to reset the screen. So now we're back, and let's say that the next part of this is about the rational root theorem. The rational root theorem is also another handy theorem that helps us find out what our roots would be, and it gives us values to check, so we don't just check values, randomly. So what we look at is we look at the last term and the leading term, and you make up a rational root quotient. So the rational roots you would check, you put all the factors of, we'll call this the p term, and we'll call this the q term. These are like, classically they define the p value and the q value, but you would put 2 over 3, and you would consider all the factors of 2 over 3 to check. So for instance, you would have plus or minus 2 and plus or minus 1. Those are the factors of 2 over the factors of plus or minus 3 and plus or minus 1. So your list of possible rational roots would be all the different combinations with these. So for example, to find the combinations, I would use 2 over 1, positive 2 over 1, positive 2 over 3, plus or minus 2 over 1, plus or minus 2 over 3, plus or minus 1 over 3, plus or minus 1 over 1. So we have basically 8 values for rational roots to check. I would always start off with the values that are the easiest to use. So whenever I do root checking, I always start out at the smallest value. So if this is 0, I'm going to try 1, and then I'm going to go to -1. And then I'm going to go to, and I'm not going to use the fractional ones. I'm going to try the integer ones first, just because it's out of, I like trying the easy ones first. And if I get lucky and find those roots work, then that will give me an easier polynomial to solve for the next round. So if I were going to do this, the first root I would check would be positive 1. So I'm going to put 1 out in front, and I'm going to use, I've got 3, 4, -5, -2, and I'm going to try that out. So I bring the 3 down, and then that's going to be 3, and that'll be 7. And then when I multiply here, I got 7, and then that would be 2, and then when I multiply that, I got 2, and look at that, I found a root. I really just got lucky. So I found a root at 1, and now I'm going to try another root. So another thing you can do too is you can just check this polynomial, because it was third degree. You can check that also and say, okay, now you got 3x squared plus 7x plus 2. Because you got to this point, if you wanted to do a quadratic formula, you could, but in this chapter, just stay with the spirit of what this chapter is about, and just try to find another root. So let's just give this one a shot. I'm going to try -1. So when I try -1, let's see what happens. So I bring the 3 down, I have -3. This will be 4. So then I'll have -4. This will be -2, and then I basically have a remainder. So that didn't work. So -1 is off the list. So I'm not gonna. So -1 is gone. So now I have to erase all my work, and I'm going to try using or finding. I'll try 2 this time. So I'll bring the 3 down, and that'll be 6. I'll bring the make 13. So now that'll be 26. And as you can see here, because I got all positive values, I know that 2 is my upper bound on the limit. So this is the upper bound, and I'm not going to try any other values beyond 2 for that. Because I got a remainder, I'm not going to keep that. I'm going to cross 2 off the list. I'll just write 2 as an upper bound, just so I don't lose that information. And now I'm going to work towards, I'm going to try out -2. I hope -2 works. So now this is, I bring the 3 down, I got -6. Bring the 6, that's -6, so that makes 1. And this will make -2, and I got 0. Okay, so I found another root. So -2 is a root. And so right now I have the root values of 1, -2, and now I can just set up a nice linear equation. 3x plus 1 equals 0. Solve for that root, and I got 3x equals -1. X will equal -1/3. So I have my 3 roots, and you can see that the negative 1/3 I would have found under my rational root theorem, but I didn't have to because I was able to depress a polynomial down to a linear term and then solve for that directly. I hope this video helps, and tomorrow in class we're going to be practicing more of this, and I look forward to hearing your comments in class. Take care.